Hello everyone, let us continue our discussion for week 6, topic 1, part 4, for the topic exponential functions. And this topic can be found on pages 90 to 92, and we will be discussing examples 3 to 7. So one of the applications of exponential functions is about population. So on several instances, scientists will start with a certain number of bacteria or animals and watch how the population grows. For example, if a population doubles every 3 days, this can be represented as an exponential function. So example number 1, let t equals t in hours. At t is equal to 0, there were initially 20 bacteria. Suppose that the bacteria doubles every 100 hours. Give an exponential model for the bacteria as a function of t. So for exponential models in population growth, suppose a quantity y doubles every t units of time. If y sub 0 is the initial amount, then the quantity y after t units of time is given by y is equal to y sub 0 times 2 raised to t small t over capital T. So since our problem involves the doubling of the number of bacteria, we will be using 2. However, if we have 3 times or 3, of course we'll be using 3 and so on. So y is the amount of time t, y sub 0 is the initial amount, t is the time elapsed, and t is the amount of time that the quantity doubles. So from the given example, example number 3, we have the same situations earlier. So the exponential model for that is y is equal to 20 times 2 raised to small t over 100. So from the given problem, the initial amount is we have 20 bacteria. We'll be using 2 because the bacteria doubles every 100 hours. We don't know the time that elapsed. Later we'll be discussing an example of that. And this bacteria doubles every 100 hours. So your capital T is 100. So when you will be asked how many bacteria are there in 400 hours, so then we will be using this formula. Okay, so we will use our calculator to solve for the number of bacteria after 400 hours. So the initial amount is, or the initial number of bacteria is 20. So this is the formula, and then times 2, and then the exponent will be, so you are asked the number of bacteria after 400 hours, so we have 400 divided by 100, which is the amount of your capital T, because the bacteria doubles every 100 hours. And therefore, after 400 hours, there will be 320 bacteria. Okay? So, after 400 hours, we have 20, which is the initial amount, 2 because the bacteria doubles every 100 hours. So 4, this 4 is from 400 divided by 100. Okay, in which we have the value of, or the number of bacteria after 400 hours. There are 320 bacteria. Okay? So how about if we have after 500 hours? So we can just change this to 500. So after 500 hours, there are 640. So after 1000 hours, there are 20,480. Okay? So let us continue. So another application of exponential function is exponential decay. Exponential functions can be used to model radioactive decay. So the definition of half-life is the half-life of a radioactive substance is the time it takes for half of the substance to decay. So let us have an example. Suppose that the half-life of a certain radioactive substance is 10 days and there are 100 grams initially. Determine the amount of substance remaining after 30 days. So still we will be using the same formula as the population growth. However, since the amount divides into 2, or it is half into 2, or it is half after 10 days, so we'll be using 1/2. Okay, so y is still the initial amount, t is the time elapsed, and t is the length of half-life. So the half-life of the given radioactive substance is 10 days. Okay, so let us use the calculator to solve for the remaining amount after 30 days. So the formula is y sub 0 is 10 grams times, we have 1/2 raised to, we have the exponent after 30 days divided by the half-life of the given radioactive substance is every 10 days. So therefore after 30 days the remaining amount is only 1.25 grams. Okay, 1.25 grams. Okay, what do you think if we have 50 days? Okay, so this is the remaining amount after 50 days. After 100 days, oh, okay, 100 days after 1000, so it's very small. So after 150 days, okay. Okay, so we have after 30 days the remaining amount is 1.25 grams. So from the initial amount of 100 grams, after 10 days we have only 5. After another 10 days we have 2.5. In another 10 days the remaining amount is 1.25 grams. Now let us proceed to another application of exponential function, which is compound interest. A starting amount of money called principal can be invested at a certain interest rate that is earned at the end of a given period of time, such as 1 year. If the interest rate is compounded, the interest earned at the end of the period is added to the principal, and this new amount will earn interest in the next period. The same process is repeated for each succeeding period. interest previously earned will also earn interest in the next period. So that is compound interest. So we have an example. Mrs. De La Cruz invested 100,000 in a company that offers 6% interest compounded annually. So how much will this investment be worth at the end of each year for the next 5 years? So for compound interest, if a principal P is invested at an annual rate R of R, compounded annually, the amount after T years is given by A is equal to P times 1 plus R raised to T. Okay, so we'll be using this formula to solve the problem. Okay, so we have A is equal to P times 1 plus R raised to T, where your P is the principal and R is the rate and T is the time. Okay, so we'll be using our calculator. Okay, the principal is 100,000. And then we have to multiply that by 1 plus the rate is 6%. 6%, so in decimal that is 0.06, and then raised to time is after 5 years. So in 5 years, the investment will be more than 133,000. Okay. So we have this amount after 5 years. For example number 6, we will be using the same problem as problem number 5, but is it possible for Mrs. De La Cruz to double her money in 8 years or in 10 years? Okay, so let us start with 8 years. Remember that the principal is 100,000. So what is asked in problem number 6 is to determine if after 8 years it would be 200,000 or not, or in 10 years would it be 200,000 or not. So let us go back to our calculator. Okay, so your 5, let us change this to 8 after 8 years. So she has only 159,000 and the amount is not doubled. Okay, after, let us see if we have after 10 years. Okay, so she has only more than 179,000. Okay, so therefore we can say that since her money still has not reached 200,000 after 8 and 10 years, then she has not doubled her money during this time. And the last one is the natural exponential function. So while an exponential function may have various bases, a frequently used base is the irrational number e, which is equal to 2.71828. Because e is a commonly used base, the natural exponential function is defined having e as the base. So remember, we have natural exponential function. So by definition, the natural exponential function is the function f of x is equal to e raised to x. So we have example number 7. A large slab of meat is taken from the refrigerator and placed in a preheated oven. The temperature T of the slab T minutes after being placed in the oven is given by T is equal to 170 minus 165 times E raised to negative 0.006 times T degrees Celsius. Construct a table of values for the following values of T: 0, 10, 20, 30, 40, 50, 60, and interpret your results. Round off values to the nearest integer. Okay, so by the way, this is T, small t, and this is capital T. Okay, so let us use our calculator. Okay, so we will enter the function. So the function is T is equal to 170 minus 165 times your E. So let us look for the value of E. So E raised to negative 0.006 times the value of D. So let us start from the value of D equal to 0. So when T is equal to 0, we have 5. Okay, 5 degrees Celsius. Okay, next we have, if the time is 10, so we have 15 degrees Celsius. If we have 20, so we have the temperature is 24. If we have 30, so we have 32 degrees Celsius. If we have 40, we have also 40 degrees Celsius. If we have 50, we have 48 degrees Celsius. And if we have 60, we have 55 degrees Celsius. Okay, so we have example number 7, and for the interpretation, the slab of meat is increasing in temperature at roughly the same rate. So again, for this video, we have discussed some of the applications of exponential functions, starting from population growth, and half-life, compound interest, and we have also discussed the natural exponential function with a base E, and those are the application of exponential functions. So I hope you have learned a lot from this video, and we'll be seeing each other next time for our next tutorial video. So that's all. Thank you very much.